we're going to try to wrap up our discussion of external flows today. So this is going to be the conclusion of Chapter 7. I have a couple of examples that we're going to use to do this. So last time I gave you a bunch of correlation equations, right, and some discussion of how they're applied, but we didn't get a chance to actually do so through any examples. So what I have planned here is one example on mixed laminar turbulent flow over a flat plate, as well as an example of flow around a cylinder with heat transfer in that case. And if we have time for it, we can get into banks of tubes or arrays of cylinders, which is just a pretty simple extension on the previous cases. So quickly, it's just a little refresher, right? The idea with turbulent flow over flat plates is this. You often, right, if you have flow coming in, what typically occurs is that you begin with a laminar boundary layer, and then at some point, right, if we were to graph the Reynolds number as a function of the distance along the plate. So here's our flat plate. A graph of Reynolds number will be linear, right? That's basically Rex is equal to U infinity times x over nu. So the local Reynolds number. And at some point, when that Reynolds number hits a value of approximately REC, which is equal to 5 times 10 to the 5th, we get this transition to a turbulent boundary layer. So it begins laminar, becomes turbulent, and as the name implies, right, this means that basically in this boundary layer we've got all this eddying and turbulent flow. And so this occurs at a position that we call the transition point. So we'll just define this point here where the local Reynolds number is equal to the critical Reynolds number as x sub c. So we have different correlations for the heat transfer that occurs in laminar flow versus the heat transfer that occurs in turbulent flow. The reason is, right, laminar flow has this nice orderly sort of sliding of different layers of flow past one another. So there isn't basically most of the transfer of heat from, for example, right, this layer of flow to the one next to it occurs through sort of a pseudo conduction, right? In turbulent flow, though, we've got this large-scale mixing, so it's much more efficient at moving heat away from a surface or toward a surface, and so it's a much better mechanism for heat transfer. Turbulent flow is. So we've got different correlations for laminar flow and turbulent flow, but the kicker here is, right, the complication is that when we have both of them, our overall heat transfer coefficient has to be a sort of a spatially weighted average of the heat transfer in laminar flow versus the heat transfer in turbulent flow. So we got that by saying, right, that the overall Nusselt number, so length, would be defined as, let me make sure I'm ready, that's invited before. All right, H bar times L over KF. This is going to be L over KF times 1 over L times x sub c times H laminar plus L minus x sub c H turbulent square brackets So what this is doing is it's just saying that where the flow is laminar, right, over a length of 0 to x sub c, we're going to use the laminar, add that to the distance from here to the end of the plate, times the turbulent h bar, and divide by L, so we get this weighted average, and build it into this average Nusselt number. So the nice thing about this is that people have already gone through the math and basically given us an expression that says, right, the Nusselt number L is equal to 0.037 Reynolds number x to the 4/5 power minus a, Prandtl number to the 1/3. And if we wanted it, right, we could do a similar thing with the drag coefficient. We would find that CFL is equal to 0.074. That should be Reynolds number based on length. Reynolds number length to the negative 1/5 minus 2a over Reynolds number based on length. And so, right, if this coefficient a is a function of where and how this transition from laminar to turbulent flow occurs for laminar to turbulent transition at critical Reynolds number of 5 times 10 to the 5th, we end up with A is equal to a static value of 871. And if turbulent flow is tripped, right? If we do something to the flow to make it turbulent from the start, so there's no laminar component, then A is equal to 0. Okay, so this we discussed this in the last lecture. We got to this point, but to drive this point home, I think there's a particularly good example in the book. This is problem 717. I'll give you guys a minute to finish writing that down, but remember that all of this stuff is also summarized in that table 7.7 in the back of chapter 7 in the book. We're going to use that in a second. So this is problem 717 from the back of the chapter 7. And the way this problem is stated is it says, assume that we've got, right, some sort of box that is like a cool compartment, maybe an ice chest, for example, that has a lid made up of 2 sections. Okay. We'll call those sections A and B. So it's basically 2 flat plates right next to one another. Each one has dimensions of 0.5 meters by 0.5 meters. And is sitting at a uniform surface temperature of 10 degrees Celsius. Okay. We've got air coming in from left to right, blowing across these 2 adjacent flat plates. This air is at 1 atmosphere pressure. It has a free stream velocity of 25 meters per second at a temperature of 35 degrees Celsius. Okay, so the right, so this looks a lot like just flow past a flat plate, right? The idea behind this segmented AB is that flat plate A has a smooth surface, and plate B, we're going to assume, has a very sandpapery, like roughened surface. Okay. So what we're going to try to do is find the heat rate Q for two configurations. For A, or we'll say case 1, so we don't confuse our plate A with case A. Case 1, we're going to have it just like it's shown in the sketch, right, with the smooth plate followed by the rough plate. And for case 2, we're going to reverse those, so we have the flow coming from left to right. With the roughened plate preceding the smooth plate. So just on observation, right, and the assumptions that we're going to use to solve this, the idea here is that by a roughened plate with B, this means that if the flow is not yet turbulent when it hits that plate, that roughness, okay, is going to create turbulence, right? It's going to be like wind over a mountain range. It's going to generate those eddies in the swirling flow and prevent any laminar boundary layer from developing. It just goes straight to turbulence. So what we're going to have to figure out is kind of painting out our strategy. For case 1, does the flow transition to turbulence when it hits B, or does it transition to turbulence on its own when it's still in the smooth plate? Okay. If it transitions on its own, then we just get to use that equation that's given to us in the back of the book, right, for the natural transition at a critical Reynolds number. For case 2, if the flow hits this roughened plate first, it's going to go straight to turbulence. And so we get to use that equation that I just gave, but with this A equals 0 used. So we've got two different sort of types of flow over the same surface, and we're going to see if it leads to different rates of heat transfer. So to kind of recall the steps that we used previously, right? There was that step 1, 2, 3, 4 procedure. Step 1 was observe the geometry. In this case, we've got adjacent flat plates, and we'll say flow over one surface. Okay, this is opposed to the last example we did, where right, you guys observed that it was flow over two surfaces of a flat plate, which led to double the drag and double the heat transfer, okay, that you'd have over one surface. So it's important to make that distinction. Reference temperature. Okay. We're going to look up our fluid properties at this film temperature, which is going to be equal to, right, the average of the air temperature and the surface temperature. 22.5 degrees Celsius, or 295.5 Kelvin. So if we go to table A4, back of the book, look up air at a temperature of approximately 295 Kelvin, we end up with viscosity equal to 1.55 times 10 to the negative fifth meter squared per second. Fluid conductivity of 0.026 watts per meter Kelvin, and a Reynolds number 0.708. Okay. We could look up the other properties as well, right? Our specific heat capacity, our density, but it turns out we're not going to need those because we're not dealing with transient conduction and we're not dealing with drag coefficients in this problem. Okay. So, it's your guys' turn. Who can tell me at what value of x the Reynolds number is going to hit that transitional magic 5 times 10 to the 5th value? Okay, this is going to determine how we take the following steps. This is going to be for, I should say for case 1, which is where we've got A and B. Does the Reynolds number reach 5 times 10 to the 5th while it's still on this plate, or once it's crossed over into the second B plate? Once it's crossed, what are you getting for that critical x value? So 0.5 meters long each. Okay. Okay, anyone have it's called a transition point, an x sub c value? 0.31 meters. That looks like the right number. So if this thing is 0.5, this plate A is 0.5 meters long, right? Then what that means is, right, it's laminar, and then it's going to become turbulent before it ever is forced into turbulence by encountering plate B. Meaning, this is going to behave like plate B basically doesn't make any difference. You know, that roughness, it's turbulent anyway by the time it hits that point. So this is going to be, right, case 1. If we wanted to draw a similar sketch of case 2, okay, the difference is going to be rough plate upstream, followed by smooth plate. Here, the flow is simply going to become turbulent right away. All right. So, let me write a transition when Rex equals 5 times 10 to the 5th, and transition at x equals 0. Okay, so the next thing we want to do is, right, our next step is to pick out the desired correlation, right? What are we actually trying to find here? Sort of zoom out and reassess. So we're seeking Q, right? Just the total heat rate, which suggests that we're looking for H bar, the average convection coefficient, which suggests that we are seeking the average Nusselt number over the entire length of combined plates A and B. Right. So turn into, well, I guess I just wrote it down a moment ago. So for case 1, right, where we have that natural transition when Reynolds number is equal to 5 times 10 to the 5th, this basically means we use right, so based on L is equal to H bar L times L over KF. It's going to be that 0.037 times the Reynolds number based on length to the 4/5 minus 871 times Prandtl number to the 1/3 power. Okay, so it's going to be 0.037 times 1.6 times 10 to the 5th power. That's our Reynolds number based on length to the 4/5 minus 871 all times 0.708 to the 1/3 power. Which is going to get us a value of approximately 2,270. Okay. So we can go ahead and extract H bar from that and then use H bar to get the total heat rate. So why don't you guys just finish off those last couple of steps. What are we getting for a averaged convection coefficient? You want to have an H bar yet? $59.02. That is, I'm getting 59.1, but that's close enough for government work. I think I rounded something off here. So 59.02 watts per meter squared Kelvin, right? For those of you that were struggling on that, the just remember the definition of the Nusselt number. Okay, right here. So we're looking for H bars just equal to that Nusselt number times KF over L. So that would be, right, the fluid, the 0.026 watts per meter Kelvin, and L here would be 1 meter. Yeah.
How did you determine it was that Reynolds?
By just because that's the Reynolds number based on the length, the total length of the plate. I mean, we know L, right? We know U infinity, and it's just sort of like if Reynolds number based on x is the local value of x, then the Reynolds number of the whole plate is just the total length of it. Okay, so then if we go ahead and apply Newton's law of cooling, okay, what do we get for a heat rate Q?
Minus 737 watts.
737. Oh, yep. Minus 730. You said 737 is what you get? Okay. 737 watts. Okay. Why the negative value? Or other way around, right? In this case,
The surface is hotter than.
yeah, because Newton's law of cooling.
Not as hot. Yeah, the air is hot.
Yep, because Newton's law of cooling written as H, right, bar A, Ts minus T infinity is positive for heat
Yeah.
out of the surface. Okay, so this indicates that there's heat entering the surface through convective heating. Okay, case 2. I'm going to leave this one more or less in your capable hands, right? The difference here is when we apply that correlation equation instead of the 871, right? We're saying that it's the case where we have tripped turbulence. So that A is equal to 0, which means we've got Nusselt number based on length. It's just going to be 0.037 times Reynolds number based on L to the 4/5 times Prandtl number to the 1/3. So I'd like to see an H bar for this and a Q for this case. Yeah. U infinity was U infinity is 25 meters per second. T infinity is 35 degrees Celsius. And let me give you all the variables again. 1.55 times 10 to the negative fifth meters squared per second. 0.26 watts per meter Kelvin, and Prandtl number is 0.708. Okay. Anyone have a Nusselt number?
3,049 or 3,050. That's like really close.
Let's go with 3050. It's cleaner. Convection is an approximate thing. I should mention that with these kinds of calculations, right, so these are fits to experimental data, right, all these correlations, and so you expect them to be inexact. How inexact depends largely on what type of flow you're looking at. For turbulent flow, for example, cases like this, 10 to 15% is sort of your margin for error on these calculations. So it's enough to do reasonable design work. Anyway, H bar. 79.3 watts per squared Kelvin, and the Q.
Minus 991 and a quarter watts.
Say 3. All right. Now, I want to poll you guys, right? The math here is easy, but the kind of the understanding of what we're doing gets a little complicated. So I want to see the show of hands who got these numbers. Well, I know you did. All right. Anybody? I guess I want to hear, where is the hang up if you're having trouble with this, because I want to make sure this is fair. Yeah.
So what I don't understand is that if the Reynolds number is like a function of x, and if x is 0, then how do you? I just couldn't find the Reynolds number for this one.
Okay. So the Reynolds number is still based on the total length. The idea here is right. So when we're dealing with like the Nusselt number based on the length, the idea is that the Reynolds number we plug in is also based on the total length.
Okay, I thought it was the critical.
Okay, no. So the critical, the idea is that if transition occurs at a critical Reynolds number of 0, which would be leading it, then A goes to 0. Okay. If transition occurs at a critical Reynolds number 5 times 10 to the 5th, that A is equal to that 871.
So it's the same Reynolds number from case 1.
Yep.
Okay.
Any other sticky points? Okay. So let's move on, try to knock out another example here. This time we're going to do flow over a cylinder. Okay. So in this case, we're going to go ahead and say, so this is going to be problem number 752, but I have modified it a little bit to make the temperatures a little easier to work with. So the idea here is we're assuming we've got a long plastic cylindrical rod. Okay. This thing has a diameter of 2 centimeters. It has a density of 2,200 kilograms per meter cubed, and it has a solid conductivity of 1 watt per meter Kelvin. And a specific heat capacity of 800 joules per kilogram Kelvin. All right. So this thing is basically it's been cooled down following it's been sprayed with some coating. Okay, and the idea is it's sitting there at a initial temperature of Ts equals 5 degrees Celsius. So suddenly, right, in order to cure this new coating, the thing is suddenly exposed to a hot cross flow at a velocity, or rather, sorry, here we call this V, of 50 meters per second and a temperature of 350 degrees Celsius. All right, so this is like we're shoving this thing into a blast furnace. So, straightforward, what is the initial rate of heat transfer per unit length of the cylinder? So, going through our steps once again. Okay, we'll breeze through these. Step 1, what's our geometry? Flow over a circular cylinder, a single circular cylinder. There are also banks of cylinders. That's a different correlation, but single circular cylinder, done. Reference temperature. TF here is going to be equal to 5 plus 350 over 2 degrees Celsius, 177 degrees, or 0.5 degrees Celsius, or 450.5 Kelvin. So, for the sake of simplicity, for a case like this, I would just look up properties at 450 Kelvin. Okay, so our air properties, rho equal to 0.774 kilograms per meter cubed. Viscosity, 3.239 times 10 to the negative fifth meters squared per second. Conductivity, 0.0373 watts per meter Kelvin, and Prandtl number equals 0.686. Okay. Calculate our Reynolds number and the flow regime. Okay. In this case, well, generally we assume that we don't have this laminar turbulent distinction that we work with in flow around cylinders, because the empirical data that's out there crosses both of those regimes. It includes both laminar and turbulent. So we just need to find the Reynolds number here so we can plug that into the correlation we're going to use. So Reynolds number based on diameter. In this case, this is going to be our fluid velocity times the diameter over viscosity. I should remind you guys one more time, we discussed this last time, right, that in the flow around a circular cylinder or a sphere, we call the velocity of this flow way upstream, we call this capital V instead of U infinity, because U infinity is actually technically, when we get a boundary layer developing on this cylinder, there's going to be this velocity distribution. Okay, U infinity is the name we give to the velocity of the flow just outside the boundary layer. So U infinity is actually affected by the presence of the cylinder itself. And so we pick another variable name, which is V. So V for a cylinder is the same thing as U infinity for a flat plate. Just understand that in both cases we are interested in the velocity of the flow far, far away from the object we're considering. The undisturbed velocity, if you will. So the choice of variable name isn't that important. The thing is that you use the right value here. So, and it'll usually be made pretty clear for flow past cylinders. So anyway, the Reynolds number based on diameter is going to be this incoming flow velocity times diameter over viscosity, which is going to be 50 meters per second times 0.02 meters, so diameter, over 3.239 times 10 to the negative fifth meters squared per second. Works out to a number 3.09 times 10 to the fourth. Okay. What correlation are we looking for? Well, as before, right, we're interested in the total heat rate, Q, which means we want the average convection coefficient, which means we want the average Nusselt number. So we're seeking Q, which again means we want H bar, which means we want Nusselt number average. In this case, we call it Nusselt number D because that's our length scale. Going to table 7.7. Remember, I mentioned that there are 3 common correlations available for heat transfer in flow around cylinders. Realistically, you can use any one of those 3, but to keep things consistent, I recommend using the one that is equation, I believe it's equation 754, and it is known as the who and Bernstein. I'm trying to remember now who the name of the first person was. Churchill and Bernstein. The Churchill and Bernstein correlation. So if we go to table 7.7, look that up, we end up with Nusselt number D is equal to 0.3 plus 0.62 times, right, Reynolds number D to the 1/2 times Prandtl number to the 1/3. So it's going to be divided by 1 plus 0.4 over the Prandtl number 2/3 all to the 1/4 times 1 plus 0.3, Reynolds number over 282,000 to the 5/8, all raised to the 4/5 power. So that's real, just bare of an equation. But we know the Prandtl number, we know the Reynolds number, and so it just becomes a matter of plug and chug. So in this case, curious to see what you guys come up with. This is an easy one to make typos on, and I've got my answer, but I want to make sure that you guys get the same thing. There we go. see a show of hands if you're getting something close to 101. Okay. So if we want to find HD, right, the averaged convection coefficient for this case over the entire surface of the cylinder, we would say, right, our Reynolds number D times K sub F over D, which is going to work out to something approximately equal to 188.3 watts per meter squared Kelvin. Let me write that out a little bit more nicely. And then finally, if we wanted to find the total heat rate, right, this would be H bar D times the surface area of the cylinder times Ts minus T infinity, okay, which would be HD times 2 pi, well, we'll say pi D times the length of the cylinder, Ts minus T infinity. Since we're looking for the heat rate per unit length, you can go ahead and divide out that L and say that Q over L HD times pi D times Ts minus T infinity, which is going to work out to 188.3 watts per meter squared Kelvin times pi times 0.02 meters times negative 345 Kelvin, or approximately negative 400 or 4,080 watts per meter. Okay. So we've got about 60 seconds exactly left. So that's going to cover most of the cases that you're going to see for convective heat transfer, right? We did laminar flow across flat plates, turbulent and mixed laminar and turbulent flow across flat plates, flow past circular cylinder. There's also flow past banks of tubes. This is something that we see a lot in heat exchangers, and we'll try to kind of revisit that topic in heat exchangers. The last announcement I wanted to make, right, is, well, two, right? Homework's being submitted via Icon by close of business today, and then this evening I'm going to post the project. The project is going to be basically this stuff, plus the fin equations that you worked with in Chapter 3. So it's going to be designing a heat sink for the motor controller on an electric car. The idea is you're going to be given a certain heat rate has to be dissipated via a heat sink, and the rest is up to you. You'll be given design constraints in terms of the size. You get to pick what kind of fins you want, whether it's circular pin fins or these flat plate style straight fins. And what you're going to need to do is use the correct correlations to find H bar for whatever that geometry is. Okay, and then you're going to use that H bar to plug into the fin equations from Chapter 3 to figure out the total heat rate those fins generate. So it's going to be up to you to come up with a fin geometry that is capable of rejecting the specified heat rate and then presenting that design, that justified design. It should be a few pages. I'll get more details in the assignment that I'll post this evening, just giving you guys a little preview. Anyway, have a good weekend.
So I have a question about this problem. I get the temperature distribution in here. It looks like this one. Because it's so small, I just ignore.
Okay, if that's your reasoning there, Okay, that looks fine. Yeah, I mean that's about right actually. I don't have the solution in front of me, so I can't tell you whether the numbers exactly are right.
Okay.
But it does become approximately linear. That's
Okay.
that's one of the points. Actually, that's the point of problem 5. Is that it shows you that you can cancel basically
Yeah,
cancel those
it's
terms out.
so small here.
Right.
So I don't know how to do B and C.
So for problem B, apply. So you know the temperature distribution.
Yeah.
Apply Fourier's law at the bottom plate. So you know. Right, you've got your temperature. It's a function of y, and you can say then that Q is equal to A times KF times dt dy at y equals 0. Right?
Yeah.
That's Fourier's law. Well, I'm saying like that's how you can find the heat rate. Okay.
Okay.
And then when you want to find H, it's going to be Q divided by A times T1 minus T2. Okay.
Okay.
And so if you put those two things together, right, then H, if you substitute that in there, then it becomes that equation you have written down there. It's just doing it in 2 parts.
Okay. Gotcha. Thank you.
Yep.
Has the second midterm been scheduled yet? Or
The second midterm, I have it tentatively scheduled for. I need to sit down and hash out a couple of changes in the schedule, but I have it. Oh, come on, that's May. I had it tentatively scheduled for like either the 13th or the 16th of April.
Thank you.
So I'll give that.